All right, so welcome to Friday afternoon. Hopefully everything's been going pretty well with this vector calculus stuff. Vector value functions that you've seen are really just like regular functions. It's just we're getting vectors out. And in terms of the calculus so far, it's just the same stuff, just more than once, right? Once for each component of the vector, with a few added bonuses like no quotient rule, but two product rules, one for dot product and cross product, and so on. So at the start of class, of course, I always like to ask if there are any questions about homework. And I know, Bradley, you started to mention one. What can I help with?
All right, so the question is, find the positive t when the vector r of t is perpendicular to r prime of t.
Okay, can you tell me which assignment it is? Because I'll even pull it up.
Yeah, it's homework 3.2, question 12.
Okay. So let me go ahead and share my screen and we'll go look at that one. So obviously this one might be a little bit different than your specific, but it at least is similar and we'll be able to talk about it. And you said it was number 12, was that correct?
Yeah.
Okay. All right, so we want to find the positive t when this vector valued function given by 4t, 10t squared, and 3t squared minus 11 is perpendicular to r prime. All right, so what are we going to do here? What might be some good steps?
Find r prime of t.
I think that's a great place to start, right? If we're going to see where this is perpendicular to r prime, we probably want to find r prime. Okay, so let's do that. And then once we have r prime, how do you tell if it's perpendicular?
It'll be orthogonal.
Okay, so it's going to be orthogonal. And what's the test for orthogonal, or the easiest test?
Dot product?
Yeah, let's take a dot product. And orthogonal means that the dot product is actually equal to 0. All right, so I think we know what our strategy is here, right? We're going to go ahead and find r prime, and then we're going to see where that is orthogonal by finding the dot product. So let's pull up a whiteboard here. And let's see if we can work this guy out. So I'm going to just move this for a second so I can get my vector. Okay, so we've got r equals 4t, 10t squared, 3t squared minus 11. All right, so there's r. So let's get r prime.
R prime is 4,
Good,
20t,
good.
60.
All right, so we got 4, 20t, and 6t. So again, just differentiating each of those things individually. Boom, we're done. So now let's dot these guys. So dotting, we just take the respective components and multiply them. So we're going to get 16t plus 200t cubed plus 18t cubed minus 66t. So there's our dot product. And since we want to find out when this is orthogonal, we're going to see where does that equal 0. So before we go any further, how are we feeling? We all right with this?
Yeah.
We're all good?
Is it when t equals 0?
Well, that is one of the values.
Oh,
There's going to be more than one. If I group like terms, I've got 218 t cubed minus 50t. And yes, t equals 0 does work. I think that was Jordan who said that. T equals 0 does work, but it's not the only solution because we can actually factor out that. We pull out that t. We now have 218 t squared minus 50. And so the other possibility is when 218 t squared minus 50 equals 0. So that factor of t does give us t equals 0. So that's definitely a solution. But there are actually two more. They're going to come from this. So t is going to be plus or minus the square root of 50 over 218. That 50 over 218 can be reduced. It's 25 over 109, which I think as far as it goes. But these are our three choices. 0, positive square root of 50 over 218, or negative square root of 50 over 218. So what this is saying is for this vector value function, if you were to look at that curve that we create looking at the ends of the vectors, there are three places where that tangent vector is going to be perpendicular to the position vector. And it's going to be when t is 0 and when t is plus or minus square root of 50 over 218. All right, so let's go see what the question asked. So let me stop sharing this and we'll go back to the other one. All right, so this one is saying find the positive t when this vector is perpendicular. So again, we had three choices. We had 0, that's not positive. And then we had the two square roots. Obviously the positive one is the positive one. So let's just see, because I'm genuinely curious. Do we need to rationalize, simplify, and so on? So I'm just going to put in square root of 50 over 218, which I'm pretty sure I remember was the number. We'll find out real fast. Oh. Well, let's see if we reduce it down. 25 over 109. Did I do my math wrong?
I think it wants you to like actually put into real numbers, maybe.
Let's try 5 square roots of 109 divided by 109. Okay. Let's see if it, I know that sometimes they give you those weird forms.
Is
Oh.
the SQRT a proper way to, like, does it accept that?
It should, except notice what it says. Enter an integer or decimal number accurate to at least 2 decimal places. This is one of those where I should have actually read closely. So I don't have my calculator on me. So if you put in the decimal approximation of the square root of 50 over whatever it was, 218, we should be good. But regardless of that specifics, does that help with the idea behind this?
Yeah.
Okay. So again, yours may have different numbers, right? Different functions,
Mhm.
but it's still the same idea.
Hey Bruce, could you show number 10? I got the process right, but I don't know. I feel like I'm missing something when I'm doing the work.
Okay, from the same set, Eduardo?
Yeah.
Okay. I really don't like having that red X. Whatever. Okay, so this one says the curves given by these two intersect at the origin. Find the acute angle of intersection in degrees. Okay, so how do we do that?
Find a value that satisfies the both vectors at the origin.
What do you
That
mean
makes
by
sense.
that?
Like if they intersect at the origin, what that numerical value of the function puts it at the origin?
Okay, so like what t values do that?
Yeah, exactly.
Okay. And what are we going to do with those, like with that, once we find the t values that work?
We'll plug it into our.
We're gonna,
Okay, so we'll plug them into the R's so that we have the R's. But how do you find the angle of intersection?
The theta equals cosine inverse of v times w over the magnitude of v times magnitude of w.
Okay, good. Yeah, we'll use the dot product. All right, so I'm just going to write down what these are so that then I can switch over to a whiteboard. So let me get this real quick. Minus 2t. And I actually think what we're going to do first is graph them. Before we dive in and start doing the numbers on this, let's actually draw the graph of these curves so that we can see what's going on. All right, so I'm going to go and change my window up here to hold tight. Go back up Desmos here. And I apologize for moving it around. I've got other Zoom features that are up on my screen I have to avoid. Okay, so let's see. Oh, except this is a 3D plot, of course. Calplot 3D. All right, so we'll go ahead and put some space curves in here. Turn this guy off. And we'll add one more. All right, so the first one was minus 2t, t cubed, and minus t to the sixth. All right, so you can kind of see that graph. I'm going to change the bounds on this a little bit. Let's go from like -5 to 5. Okay, so there's that curve. The other one, we had sine of 3t, sine of minus 3t, and then t. And again, let's go -5 to 5. Turn that on. All right, so that one looks very much like a helix. If I kind of rotate things around, except it's not exactly a helix. Notice how that second one just kind of does a sine, but back and forth, up and down. And then the other one has some sort of a weird bend, right? So you can see that it kind of starts down here, works its way up and around, but in the process, it's kind of bending. Okay, but regardless, they definitely do come together at the origin. You can see it. And so we want to find the angle between them. All right, so there's the graph. So let's start with, when are we at the origin? What t values bring us to the origin for each one of them?
0.
Okay, and it's 0 for both. The way I do this is, like, look at this first guy with the minus 2t, t cubed, and minus t to the 6th. I look at this and I look at just the x component first, and I see minus 2t. I need to know when that equals 0. So I literally just take negative 2t, set it equal to 0, and that gives me t equals 0. And then you can see plugging that into both of these make them work as well. For the second one, I'm actually going to ignore the first two, because sine is going to be 0 lots of different times. It's going to happen when what's inside the sine is 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, and so on. But if you look at the z component, the only way that that equals 0 is when t equals 0. And you can see that that makes both of these also 0, because you get sine of 0. I know for this one that might have been kind of silly, and you can just look at it and see that t equals 0. But for ones that are a little bit more complicated, it's good to be able to figure that out. All right, so either way, we know that we're going to be at t equals 0. All right. So now, let's go ahead and go back to my open math. No, sorry, wrong page. This homework. All right, so we want to find the acute angle of intersection. So we're going to use the dot product. But we're not going to dot R1 and R2.
We're going to dot R prime and R prime too.
Right, we're going to dot the derivatives. Why are we going to dot the derivatives and not these?
I actually don't know why.
Okay.
Because.
Just because? That's a good dad answer. Seeing your dad, practice that one. Just because.
Well, if we dot the derivatives, we're dotting the tangent vectors, right?
Right. And that's the key, is that the derivatives are tangent to the curve, which means they point in the direction of the curve. So if we dot the tangent vectors, we're going to find the angle between the directions of the curves. If we dot these, we're going to find the angle between the two vectors themselves. But the two vectors themselves are just the 0 vector. They're the same. And they're the same because we're at the same point. So what we need to do is get R prime, excuse me, for both, and then dot those.
So we're going to dot R prime, just R prime, and not at t equals 0.
Nope, we're still going to be at t equals 0. But we need to find R prime first before we plug in 0.
Okay.
Because if we plug in 0 right now, we have constants.
Right.
We have constant vectors, and their derivatives are 0 by definition. That's not what we want, though.
Mm-hmm.
So let me go to a whiteboard again. And let's get these. All right. So can we all see the whiteboard?
Yeah.
Okay, let me just clear it all off. All right, so R1 prime, the derivative of that one's going to be minus 2, 3t squared, and minus 6t to the fifth. R2 prime is going to be 3 cosine of 3t minus 3 cosine of minus 3t, comma 1. So now when I plug in 0, because that's where we are, t equals 0, we have R1 prime is minus 2, 0, 0, and R2 prime is 3 minus 3, 1. So always differentiate first. Always do this part first before plugging in your t's. Because as soon as you plug in t, you make it a constant, and the derivative goes to 0. All right, but now we're ready. We know the cosine of this angle is going to be R1 prime dotted with R2 prime divided by their magnitudes. So if I take this dot product, I'm going to get minus 6. And then I need the magnitudes. The magnitude of R1 is 2. And the magnitude of R2 is the square root of 19. Right, you square each of these and take the square root. So 9 plus 9 plus 1 is 19. That's square root. All right, so then theta is just going to be whatever the inverse cosine of that is.
Since it's an acute angle, we can just assume it's positive in this instance.
Yes. Yeah, because when you do this, when you do the inverse cosine, you are going to get a number that's between pi over 2 and pi, right? Because it's second quadrant. So basically, you're finding like that guy. The acute angle, of course, would be the reference angle. And so, yes, if you went with positive 6 over 2 root 19, whatever angle that is the acute angle. Or take this number and then subtract it from pi, or heaven forbid, 180 degrees. I feel dirty just saying that. All right. So, better for that one?
Yeah, thank you.
You good with that, Eduardo? Okay, good. All right, I'm going to go ahead and stop sharing then. Come back to this view. All right. So hopefully that was a good little review of some of those homework questions. Before I step away, actually, though, are there any more? Feeling all right?
Homework 1, problem 9 was giving me a little bit of trouble, but I mean, I can
Okay,
keep working.
we can go take a look at that.
3.1, I mean.
Yeah, I got that. Man, super slow today, my computer. It's like it's a running back for the Raiders.
Yeah, he got the hat trick. Keep talking.
Look, it's not my fault I don't like the Raiders. I grew up in Colorado,
It happens.
and when they stole Lyle Alzado from the Broncos, that sealed their fate. And I know most of you are like, who? Yeah.
I mean, I sort of know how you feel. I grew up with a Charger fan my entire life. That was weird.
All right. So does this look right?
Yeah.
Okay, so that's for you, Matthew. So find a parameterization for a circle of radius 5 with center -5, 1, -2 in a plane parallel to the xy plane. Write your parameterization so that the x component includes a positive cosine. All right, so we've got quite a few restrictions here. But if we're going to talk about a circle, obviously you need to have a center and a radius. So there's our center and there's our radius. But they have to give us a little bit more because there are lots of circles that will do this. You can tilt that circle any way you want, right? And that's why they gave us this. We need to be in a plane parallel to the XY plane. So think of the XY plane as your piece of paper. And so we just have to be parallel to that. We can be above it or we can be below it, but we need to be parallel. Okay, so basically that circle, you can just imagine if we were to draw this circle in the XY plane, and then we just raise it or lower it to wherever we need to be. All right, so I'm actually going to start with the easiest one, and that's Z. What is Z going to have to be?
-2.
Yeah, that's just going to be -2. And that's because we're in that plane. The XY plane is Z equals 0. So if we're parallel to that, it's going to be Z equals wherever we happen to be. All right, so that's the easy part. So now let's talk about that circle. So I'm going to go back to a whiteboard. Go ahead and clear it off. And now let me show you what I mean. All right, so we're centered at -5, 1. So let's say that's our center. And then we've got a radius of 5. So that means we're going to come over here, up there, down there. Whoa. Okay. Free drawing circles is bad enough for me. On the whiteboard, they're even worse. All right. So there's our circle. So basically, we want to parameterize this. And they did say we want positive cosine, I believe. It was positive cosine for our x.
Yes.
So let's do this. Let's just imagine a unit circle. How do you parameterize a unit circle?
Cosine t is x and sine t is y, generally.
Okay. Yep, good. So it'd be cosine t and sine t. Or you could have sine, cosine, or whatever, but this would do it. And so this is going to give us one that goes around this way. So let's start adjusting it. What if we have a radius of 5? How would you change this?
5 cosine t, 5
Yeah.
sine t.
There you go. Yep, just multiply it by 5. Because again, think about what happens with vectors when you multiply by a constant. is it just increases the length, and that's all we're trying to do. Instead of going out to 1, we're trying to go out to 5. All right, now we need to shift it. Now we need it so that we're over here at minus 5, 1.
Add 5 and add 1.
Okay, so we're just going to take care of those 5 and 1 by adding them. But for the 5, we're actually going to subtract it. So we're going to have 5 cosine of t minus 5. Then for the 1, we're going to add that. So now just kind of follow it. Plug in t equals 0. We're going to get 5 times 1 minus 5, which is 0. So we're going to get an x of 0.
Bruce?
For the y, 5 times 0 plus 1, which is 1. Go to pi over 2. This becomes 0 minus 5. Oh, whoops, we're going the wrong way.
Yeah, Bruce, shouldn't it be plus 5 minus 1? If it's centered at negative 5, 1, aren't you subtracting the value of its center coordinate?
I'm pretty sure I want it like this, because think about what cosine does. Cosine goes between 1 and minus 1. And so when it's 1, I get 5 minus 5, which is 0. So that's telling me the biggest my x is going to be is 0. If cosine is negative 1, then I get minus 10. So my x's are between 0 and minus 10. And similar here with y, if sine is equal to 1, then the biggest I'm going to get is 6, which would be I'm at the top. And then the bottom is going to be minus 4, which would be at the bottom. But I think what I've got going on is my orientation is such that I'm going in reverse. I'm going clockwise. Because plug in 0 and we're over here. Right? That's t equals 0. If we plug in pi over 2, I get an x of minus 5. Oh no, I'm good. Hold on. So I get an x of minus 5, and then my y is going to be 5 plus 1, which is 6. So I'm up here at t equals pi over 2. At pi, cosine is negative 1, so I get negative 10 for my x. Sine is 0, so I'm at 1. So that's at t equals pi. And then 3 pi over 2, I should be down there. And repeat, 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 repeat. Now, I know why you're thinking you wanted to subtract that. I know exactly why you're thinking that. Because when you go to the form for a circle in rectangular, this would be x plus 5 squared plus y minus 1 squared is equal to r squared, so is equal to 25. But what we're doing is we're basically making use of the Pythagorean identity. And so we want x plus 5 to equal 5 cosine. And we want y minus 1 to equal 5 sine. So that if I were to replace in here, I would get 25 cosine squared plus 25 sine squared, which equals 25. And that's why if I solve for x and y, I have to subtract the 5 and I have to add the 1. So it's opposite of what you've been doing because we're approaching it a different way. We're basically solving for x and y. And so if you're going to isolate that x, before when you subtracted, right? X minus h. If you solve for x, it's going to be x equals whatever plus h. And similarly for the y, it'll be plus k.
I gotcha. Thank you.
So it's a little bit funky, no doubt, but that's where it is. So this is another good tip for you. You notice that when I built this, I started with something simple. I went to, let's go to unit circle. And then I slowly made it more complicated, more in tune of what we were looking for. And then once I had this, you notice that I checked it. I plugged in t values to see if I was actually getting what I wanted. So that's a big recommendation I have if you're ever trying to parameterize, is go ahead and do that. Start with something simple. And then once you get where you think you're supposed to be, double check it. Plug in a couple t's.
And the z value is a fixed number because of the fact that we're parallel to the xy plane.
Exactly.
Okay.
And had we been, let's say, parallel to the xz plane, that's y equals 0. So then our y component would have been constant. Same thing if we were parallel to the yz plane, then the x would be constant. If we were told we were in some other plane that was slanted, it would be a much more difficult question. But then we would have to relate x, y, and z using the equation of the plane.
Okay.
Yeah.
Thank you.
You're welcome. All right. So cool for homeworks. All right, so don't forget that those things are due Monday night at midnight. So we'll still have one more day together. On Monday, if you guys have more questions, you can ask and we can chat a little bit more about them. But just be aware, you want to make sure you're working on them. And it is just the first 2 sections. We've talked about just about everything from there. We have a couple more things from today, but it's really straightforward. So we're going to finish up 3-2 and then start moving on to newer stuff. So, all right, well, I'm going to go ahead then and head over to the whiteboard. So I'm going to end this screen and I'll be right back with you on the other side. All right. So let's just kind of recap where we were last time. We were looking at vector value functions, and we got to the point where we saw limits are done exactly the same way as regular functions. We just do it once for each component. And then we saw the derivatives done exactly the same way, again, once per component. And so let me just remind you some facts that we saw about the derivative. All right, so we've got that r prime is orthogonal, or not, sorry, it's not orthogonal, is tangent to the curve. This is a huge, huge important thing. And in fact, we made use of that today when we were looking at that one homework problem, right? About finding the angle between those 2 intersecting curves. It really came down to what is the angle between those 2 tangent vectors. So we will use this a lot, but this is probably the most important fact about r prime. Okay, so it's tangent to the curve. Another one that is important, we saw that if r dotted with r is constant, then r dotted with r prime is 0, right? Meaning that r prime is always orthogonal to r. And so I know that we saw an example of this. I forget which function we did, but we saw that, right? So another kind of nice fact. In terms of all the rules, they're the same. Meaning things like scalar, product rule, chain rule, and so on. There were just a couple of weird, quirky things. We now have 2 product rules because there's one for the dot product and another one for the cross product. Their structure is identical. Just be careful with the cross product because the cross product is not commutative. You need to make sure you have that in the right order. So there are 2 product rules, but there's also no quotient rule. So that's kind of nice. Although some of you may be to the point where you don't even use a quotient rule anymore. I was actually just talking to my son about this, and he was like, well, quotient rule is stupid. You don't even need it. You just do product rule with negative powers and it's faster. And I was thinking to myself, oh my God, it's like I'm talking to myself. This is crazy. But anyway, because I'm the same way, I never do the quotient rule. But anyway, so we saw these rules, just some facts to kind of remind you. I'm not going to talk anymore about actually doing the derivative because it's just the same as before, and you guys already know how to do that. All right, but I do want to talk about this tangent vector-ness, the fact R is a tangent vector, because it is so useful. One of the things that we like to do is define what we call the principal unit tangent vector. So that's awful. But each one of these words, of course, means something. So obviously it's a vector. It's going to be tangent to our curve. What does unit tell you?
Magnitude of 1.
Okay, so it's got a magnitude of 1, so it's got length 1. So we're looking for a tangent vector that's length 1, and then principal just means it's the main one, right? The primary one. So let's think about a curve and what this is going to look like. So you got some sort of curve here. And we saw that at some location, like right here at this point, we get R prime, and the R prime is tangent to the curve. And it points in the direction of the vectors are progressing, right? So if this is the parametric curve, its orientation would be curvature. All right, so first of all, let's talk about principal. Because there's more than one vector that's tangent to this curve. There's actually a whole bunch. There are actually 2 primary ones. There's also the one that points in the opposite direction. But technically, even with a space curve, you could have one tangent to this that's pointing off in any kind of weird direction. So we have to pick a standard. And so the standard is in the direction of travel. Okay, so for principal, we're going to pick in the direction of travel. If you ask me why this was done, my answer, I mean, I could give you the answer because I don't actually have an answer to that, but my guess is because it's really easy to find a vector that points in the direction of travel. You just take a derivative. All right, so that's going to be the chosen direction. So we can actually use R prime to help us that. We just have to make it length 1. So how do you vector length 1? Remember the vector uniter?
You divide by the magnitude.
Yeah, you just divide it. Okay, so this is how we're going to define this principal unit tangent vector. We use capital T to represent it. And so we're going to find it by taking r prime and dividing by the magnitude of r prime. So dividing by the magnitude makes it length 1. Using r prime makes it tangent and also principal. So it's principal unit tangent vector. All right, so let me show you how this is done. Let's do a specific example of a 3-dimensional curve, and we will find the unit tangent vector. So we'll go back to one that we've seen before. Let's look at this guy, where r is cosine, sine, and t. Do you remember what shape that was?
Helix.
Yeah, that was that helix. So we're just going in a circle and we're coming out towards you, right? Okay, so let's find the principal unit tangent vector. So we'll start by going with r prime. That's going to be minus sine t, cosine t, 1. So then we need to get the magnitude of r prime. So that's going to be the square root of sine squared plus cosine squared plus 1. Sine squared plus cosine squared, of course, is 1. 1 plus 1 is 2. So we get that this magnitude is the square root of 2. So we'll go ahead and multiply this vector, r prime, by 1 over root 2. And so here is our unit tangent vector. It's minus sine t over root 2, cosine t over root 2, 1 over root 2. So you give me a t value, you tell me where we want to be. You give me that t value, I plug it in here, and I can tell you exactly what the unit tangent vector is and give it its coordinates. So again, this points in the direction of the curve, and it is length 1.
How'd you get the root 2?
So I used the Pythagorean identity that sine squared plus cosine squared is equal to 1,
Oh,
right? That
okay.
one of those fundamental trig identities. So that's just 1, and of course 1 plus 1 is 2.
Okay.
All right, so any other questions on this example? So just notice that this is a function of t. This is a vector value function as well, right? It is a vector that's determined by some t value that we plug in. So big T, the unit tangent vector, is itself a vector value function. So it's a vector value function that we get from another vector value function, but it just has some specific use. All right, specifically, it's always going to be tangent and length 1.
And it won't always be a vector valued function, right? Depending on certain ones.
Oh, no, it always a vector valued function. Even if there is no little t in here anymore, even if these are all constants, that would mean that your tangent vector is always pointing the same direction, right?
Yeah.
That's still a vector valued function. It's just a constant vector valued function.
Oh, okay.
So the reason I can tell you that it's always a vector valued function is because it's a vector. It's a vector that, no, yeah, it's a vector. And if it's got a little t, then for sure it's clear that we can see that it is a function. All right, so far so good. That's big T. Now, interesting fact about this. Check out what happens if you dot T with itself. So let's just run up here and let's take T and dot it with itself. So that means we're going to take r prime over the magnitude of r prime. We're going to dot it with r prime divided by the magnitude of r prime. Now, those two magnitudes are scalars, right? They're just numbers. So we can kind of pull those out of the dot product. So we're going to get 1 over the magnitude of r prime squared. And then there's going to be times r prime dotted with r prime. I'm just the definition of big T. And I'm taking big T and dotting it with itself. All right, so do you remember what happens when you dot a vector with itself?
It's a constant, right?
Not always a constant. If it's a constant, we like that, right? Because then we can make use of the fact that its derivative is normal to itself or to the function. Okay, well, think about this. Let's go to definition of the dot product. So here's a vector, right? Let's just call it F, G, and H. So if we dot it with itself, we're going to get F squared plus G squared squared, right? Well, how about this? What's the magnitude of V? It's the square root of F squared plus G squared plus H squared. So when you dot a vector with itself, you actually get the square of its magnitude.
So 1.
A little aside. Yeah, so check out this guy, the unit tangent vector. Since I've got r prime dotted with r prime, well, that's just going to be the magnitude of r prime squared. We already have 1 over that magnitude squared. So it equals 1. So let me just put a little line here so that we keep these things separate. So what we see is that this unit tangent vector, when dotted with itself, you always get 1. So more importantly, you get a constant. All right, so this is when the little flag should pop up, the alarm bell should go off. You go, oh, wait a minute. Nice things, if a vector dotted with itself is constant, we know that its derivative is going to be orthogonal, right? It's going to be orthogonal to this. Well, we're going to use this fact to create what we call the principal unit normal vector. Okay, so just the words, and it tells you exactly what it is. It's a vector that's normal to the path. Okay, it's not tangent to the path, it's normal to the path. It is length 1, and it's the principal one. It's the primary one, the one that we're going to pick. All right, well, here's how we're going to create it. We know that big T derivative is normal to the curve. Because of this fact over here, right? The fact that T dotted with itself was a constant. So we attach that to that theorem that we did last time, and we know that T prime is actually normal to the curve. Okay. So to make it principal, we're just going to go in this direction. Again, we have to pick one of the vectors that's normal. So we might as well use the one that's easy to get, right? T was pretty easy to find because we just took the derivative. We just made it length 1. This one, similarly easy to find. We're just going to take the derivative of big T and normalize it. So this vector we use big N for. So the unit normal, principal unit normal vector is a big N. And we define it as the derivative of T divided by the magnitude of the derivative of T. And so if you look at this and compare it to how we defined big T that I erased just a moment ago, it's identical, except we're using big T instead of R. So we're really just doing the same thing. Yeah, go for it.
N refers to the derivative of T.
So big N is not just the derivative of T, but it's the derivative of T divided by its magnitude.
It's
so
the
it
norm.
points in the same direction.
Okay.
Yeah, it points in the same direction as the derivative of T. But we make it for 1 by dividing by its magnitude.
Gotcha.
All right, so let me just show you how we find that with that same example we did just a minute ago. So if we go back and we look at that one again, we had R was cosine, sine, and then T. So we found that T, big T, was minus sine T over root 2, cosine T over root 2, 1 over root 2. Right, so we just did that example a little bit ago. But this helix, we saw that this was the unit tangent vector. Okay, now let's find n. So we're going to start by getting t prime. So t prime, it's going to be minus cosine of t over root 2 minus sine of t over root 2, and then 0 for our last component. So there's big T prime. Now, I know that n points in this direction, but I need to normalize it. I need to make it length 1. So let's get the magnitudes. So the magnitude of t prime, that's going to be the square root of this thing squared. So cosine squared t over 2 plus the second one squared. So sine squared t over 2 plus 0 squared, which is 0. And I'm going to do the exact same trick that I did last time using the cosine squared plus sine squared is equal to 1. So this is equal to 1 over root 2. So big T prime, its length is 1 over root 2. So to get n, I need to take t prime and divide it by this. So we're going to have minus cosine of t over root 2 divided by 1 over root 2, comma, minus sine of t over root 2 divided by 1 over root 2, comma, 0 divided by 1 over root 2. But if I simplify that, those root 2's cancel, and I'm left with n equals minus cosine of t minus sine of t. and then 0 is my third component. So for the third valued function that we started with, that was cosine, sine, and t, the two most important vectors that are associated with it are big T and big N. So big T points in the direction of travel, and it's length 1, and then big N is normal to the curve, also length 1. So hopefully you're seeing that the process for finding big N is like identical to finding big T. We're just using a different function because we've now got a different vector. But I am going to warn you that finding big N can actually be really cumbersome sometimes. This example that I just showed you is actually really, really nice because the magnitude of r prime was constant. When we went back, when we calculated it, we saw the magnitude of r prime was the square root of 2, right? Nice and constant. If it's not constant, that means these denominators have t's. And now when we differentiate, it's going to require product rule. And not only is it require product rule, but you're going to have square roots of stuff. So it get a lot more complicated. Let me show you an example real quick. But before I do that, any questions on finding n? Are we good with that? Okay, I'm going to assume we're good with this guy. All right, thanks for the thumbs up from a couple of you. All right, so let me do another one that on the surface doesn't look that bad. You're going to go, what's the big deal? It's a super easy function. You'll see what happens when we go and we find n. All right, so let me change this. Let's go to r equals t squared, t cubed. So no deal. Super simple function. I mean, it's just polynomials. It's just powers. It's super easy, right? All right, so let's go and find big T and big N. So I'm going to leave a space here. T equals, we'll do this next. So let's get big T. So we got to get r prime. All right, well, easy means easy derivative. So we have 1, 2t, and 3t squared. And then we need the magnitude of r prime. All right, well, that's 1 plus 4t squared plus 9t4. All right, so in order to get t, I just have to take r prime and divide by that magnitude. I'm actually going to go ahead and write it down here. So that t equals 1 over the square root of 1 plus 4t squared plus 9t to the fourth. That's the x component. The y component is 2t over that same square root. And then the z component is 3t squared divided by that same thing. All right, so there's big T. Go ahead and put a box around it. All right. So now we're going to find big N. So what's the first thing we have to do?
T prime.
Yeah, we got to get T prime. And it's at about this point you should start going, no, I don't want to. Because think about that. Now, if we're going to differentiate these, well, this first one's not terrible. I mean, I guess it's to the minus 1/2 power. So let's see, T prime is going to be, for the first component, minus 1/2 times 1 plus 4t squared plus 9t to the fourth to the minus 3/2 times the derivative of what's inside from the chain rule, which is 8t plus 36t cubed. All right, so there's the derivative of the first part. The second part, we're going to have to use quotient rule. So strap in. Let's see what happened here. So we take a derivative of the top, 2 times the bottom, square root of 1 plus 4t squared plus 9t to the fourth, minus the derivative of the bottom, 1/2 times 1 plus 4t squared plus 9t to the fourth to minus 1/2 times what's inside it, 8t plus 36t cubed, times the top, 2t, divided by the bottom squared. Well, I mean, that's nice. The square root went away. So there's your second component, comma. I clearly don't have enough space, so let's run it up here. We'll get our third component. Got to use the quotient rule on this last guy. So derivative of the top, 6t times the bottom, all square root is this, minus the derivative of the bottom, which I already have here. It's 1/2. 1 plus 4t squared plus 9t to the fourth to the minus 1/2 times 8t plus 36t cubed. And I apologize, this will be really hard to see. Try to make it as clear as possible. Times the top, so times 3t squared, and then that is all over the bottom squared. So again, the square root went away. Beautiful. All right, so there's our third component of T prime. I'm sure that there is a way to simplify, right? All this nonsense, we can probably simplify it down. But even if we do, we're not done, right? What do we have to do at this point?
Find the magnitude.
Yeah, we got to get its magnitude. We got a magnitude of nonsense thing. And then divide this by that magnitude. So this is what I was kind of getting at when I warned you guys, when I was like, hey, the example I showed you was really nice. They can get really gnarly really fast. This is a great example. And look at what started with. It was nice, right? I think you guys were probably all really happy to have an R like that. Well, finding N specifically can get really, really messy, really, really fast. So my suggestion is always simplify as much as possible. Now, for those of you guys who know me, you know I like to say that calculus isn't hard. It's the algebra that's difficult. This is a great example, right? The calculus isn't tough. This whole idea of differentiate and then divide by the magnitude, that's easy. But the algebra that we need to do to get to something that's even useful is kind of a pain. All right, so, but that's big N. I mean, that's how we find big N, is by doing the derivative of big T and then dividing by 2. So you probably don't feel very fulfilled with this, especially since I just kind of stopped and punted. But it's too short to slug this sucker out right now. I'll show you later some tricks on how you can find big N, especially when we're at specific points. Because in an applied situation, that's what we're going to be concerned with, right? Is finding big N for a specific thing. And if you already know big T, there are ways of finding big N faster when you're at a specific location. And I will show you that later. Those who know me know I'm good at sharing those kinds of tricks. So, but we need to know a little more information before that's even useful. Okay. So speaking of said information, let's start by talking about where does big N point? Because we already know where big T points. It points in the direction of travel. So the question is, what about big N?
Perfectly
Now,
away.
we're going to figure that out. I'm sorry, say again.
Perfectly away.
What do you mean by perfectly away?
Isn't it orthogonal to the T?
Okay, so it's going to be orthogonal to T.
Mm-hmm.
Well, because here's where I'm going. So Bradley, here's a curve, right? And let's say we're at some point and we've got, say, T, right? So T is pointing in the direction of travel, so the big T. So big N is going to be orthogonal to this. So what did you mean by perfectly away, like in this picture?
Like, it's just like gonna go away from T, pointing up in this instance.
Okay, so pointing at, so like that?
Yeah.
Okay. All right, because that's definitely one of the choices, right? That is orthogonal to T.
Could
There's
point
also
down,
the one that's
though.
pointing down in this case,
Yeah.
right? That's still orthogonal. And those aren't the only two, because how about the one that's coming out of the board? That's orthogonal.
Yeah.
I mean, there are, again, an infinite number of orthogonal vectors. So kind of like with the tangent vectors where we have to have one that points in a specific direction, the question is, where is big N point? To help us figure that out, let's actually find big N for a nice function. Okay, we're going to go dimensional. Let's just go with cosine sine. So this is nice. You'd all know exactly what it looks like. What is it? What is this curve?
Isn't it just a circle?
Yeah, just a circle. It's a unit circle.
Unit circle.
Right? So it's a unit circle centered at the origin. Oh, and I just realized some of you might say, oh, you should all know this. Some of you might go, well, shit, I don't know this, and start feeling like crap. Don't take that this way. Like, that's not what I mean. Say you all know this. Not as a, if you don't know this, then you're not worthy. That's not what it means. It's something that we see a lot regularly throughout math. And I try to point these out so that you start recognizing important structures. Like this one's a huge structure we see all the time. So anyway, so that's just circle, unit circle, no big deal. All right, let's find big T and big N. And I promise these will be easy. So to get big T, we need to start with R prime, which is negative sine cosine. The magnitude of this is the square root of sine squared plus cosine squared, which is 1. So it actually is already big T. So R prime is big T because it's unit. So then if we want to find N, we need to go to T prime. That's just the derivative of this, which is negative cosine, negative sine. Again, its magnitude is the square root of cosine squared plus sine squared. Boom, which is 1. So that guy is also N. So let me just put a box around the important things here because I know there's a lot written and it might help us find what we're looking for. But there are big T and big N. So let's draw the circle. Let's look where these guys are and what direction they're pointing and all that. So we already know about T. We've seen enough of this that it's pretty clear. So we've got our unit circle. So if I were to choose a location somewhere, like right here, there's T. All right, so which direction is N point? Well, I'll help you out. We're actually not going to plug in numbers or anything. We're just going to compare this to R. So look at R and look at big N. What do you notice about them?
They're opposite.
They're
Opposite
opposites because they
sides.
point in opposite directions,
Mhm.
right? So you got opposite signs because they point in opposite directions. So where did R point? R went from the origin out to the circle. So where does N point? Well, opposite direction, right?
I was muted
So that means it's going to go from the point on the circle
to the origin.
towards the center. So on this unit circle, N is always pointing back towards the center. And it doesn't actually matter where we are, right? Because these two things are opposites regardless of T. No matter where we are on the circle, N is always pointing inward. So for this example, we see that N is pointing toward the interior of the curve. And that's actually the case always. So no matter what our function is, if it's base curve, the N is always pointing towards the interior of the curve. So back to this example, or the first one I just kind of threw up with a random drawing, N is actually going to be the one that's pointing downward, length, because it's the interior of that curve. If I were to move her to, say, this point, now I've got a different unit tangent vector, but this time the normal vector is going to be pointing upward because it's the interior of that curve. Just imagine fitting a circle to the curve. So wherever you are, think of a best fit circle. The N is always pointing towards the center of that circle. So think about this second point I just drew, right? There's a best fit circle. Pretend it's a circle. I don't have space to make it actually a circle, but this would be like the best fit circle. And you notice that N is pointing towards the center. It won't necessarily reach the center. It would only reach that center if that circle was radius 1. I mean, that's what was going on with our unit circle. But at least is pointing towards the center or through the center. So to help you see where N is and how N is pointing, it's always pointing towards the center of the circle. Obviously, if we don't have a curve, if it's just a line or a linear segment, N is a little bit more difficult to find. Turns out N is actually the zero vector in that case. But graphically, this can help you see where N is. So just like T, it always points in a special direction. It points towards the center of the curve, center of the circle that would define our curve at this point. So for you physics types, And yeah, I'm looking at the like 7 of you that were in my physics class last quarter. Are you starting to see why N and T might matter? What did we talk about last quarter that N and T are related to?
Rotation.
Okay, rotation and specifically
thinking-
what?
Yeah. Acceleration.
Yeah, it all comes back to acceleration. Remember your accelerations? We always broke acceleration into 2 pieces. There was tangential acceleration and there was centripetal acceleration. Tangential acceleration is what changed your speed. Centripetal acceleration changed the direction of your velocity. The centripetal acceleration is always pointing in the direction of n. The tangential acceleration is always pointing in the direction of big T. And so you can imagine if we have a more complicated path, that's out there in space, and you wanted to be able to describe the acceleration, well, you go, okay, well, which type of acceleration? So you go, well, centripetal acceleration. Knowing n is big, because then you just have to multiply it by the right magnitude to get what you need for your centripetal acceleration, and likewise for your tangential acceleration. So even though it seems at this point that we're just talking math for math's sake, there's huge application of big T and big N when it comes to physics. Okay, big T, that's going to always be in the direction of your tangential acceleration. And big N is always centripetal. It's centrally pointing. Anyway, just a little bit of extra about N. Now, next week, because we have a little bit more we need to talk about before we get there. Next week, we're going to start talking about curvature, which is how bendy a path is through space. And it's going to come back and be related to this kind of stuff. All right. But these guys, big T and big N, they are aligned for any kind of function, at least those that can differentiate, and we'll see them again. But the last thing I want to talk about today, to kind of wrap up our calculus of the value function, is about integration. So we've eliminated continuity, we've now differentiated. So the last question is about integration. But I know all the art. How we integrate vector value functions.
I'm guessing it's the same.
Yep. So Victor just put chat box same. Seamus just says same. Yeah, it's the same thing. We're going to integrate like we've always done. We're just going to do it 3 times. All right. So if we've got a vector, let's say it's given by f, g, and h as the component functions, then the integral. So again, we're going to write it like we normally do. So it's going to be the integral of r dt, right? Because we're integrating respect to t. It literally is just the integral of each of the component functions in their respective spots. Yay. Right? Integration is integration. We do it exactly the same way. Okay, but I forgot to put something on here. What should be here that I didn't put?
Plus C.
Yeah, are going to plus C, right? So when we integrate, if there are no bounds, we're going to have plus C. So we are going to do that. We're going to put a plus C. But the big difference is this is a C vector. So it's an arbitrary constant vector, which means it has 3 arbitrary constants. One for each of the components, x, y, and z. But you can see why those happen, right? Like think about this. We're going to integrate the first function, f. That's going to give us plus c, call it c1. The next one's going to give us a plus c, call it c2. The third one's going to give us a plus c3. Second vector would be c1 comma c2 comma c3. So we're going to combine them all and we're going to integrate like normal. We're just make sure that we on a constant vector, not just constant scalar. If we have bounds, so let's just, for the sake of doing, I'm going to save space and time by just writing some bounds on here. Like let's say we're going to integrate from some time values, a. All that does is put those bounds on each one of our integrals. And of course, now that's going to eliminate our plus c, because if we do a definite integral, then there is nothing to add. All right, so let's do one. We'll go back to that nice function that we were trying to find the n for, and it got really nasty really fast. Let's just go with good old r of t equaling t squared t cubed. And let's go ahead and integrate this thing. So it is this fast. You're going to get t squared over 2, t cubed over 3, t to the 4th over 4. And then we add on to it an arbitrary constant vector. You may recall that you could actually find what these pluses were if you knew a little bit about the function, right? Like if you were given some initial conditions. And the same is true here. Like if we were told that this curve goes through a certain point, has a certain vector, we could plug in that t value, use that to find c. But in general, we're just going to put plus c with that arrow, right? To make sure that we see that it's a vector, not a scalar constant. Similarly, to integrate this thing from 0 to 1. So now we would actually just evaluate these at the bounds 1 and 0. So we would get 1/2 minus 0, which is 1/2. 1/3 minus 0, which is 1/3, and then 1/4 minus 0, which is 1/4. And so the definite integral from 0 to 1 of the same function would be 1/2, 1/3, and 1/4. So like I said, it's exactly the same. We're just doing 3 different integrals, one for each of the components. All right, so process is easy enough. Making too simple. I mean, what's going to be hard? Honestly, going to make this integration hard.
Just the function.
If the individual, if the vector functions are difficult to integrate.
Right. I give you things like t sine t, and then you go, well, crap, I got integration parts. Or I give you something with like a 1 over 1 square root of 1 minus t squared, and you go, ah, shit, trig sub, or whatever. Right? That's what makes these challenging, is just the individual functions. The process itself is the same as before, just once for each component. Okay, but what is this actually giving us? Like back in the day, when you first learned integrals, what did an integral actually tell you? What quantity was it giving you?
Either acceleration, position, or velocity. Oh, that early. Yeah,
So allow
Victor's
us
right.
to-
Very under a curve.
Yeah, so like if it was a, if we just had like the function and we anti-differentiate, it's giving us like a good example, acceleration, integrate gave us velocity, integrating that gave us position, and then name wrong vector, it should be v. So vector said it get a curve, right? When we first taught you all,
we went with that. Well, we're looking at the area under curve. Using what Lee is doing is just adding up all the things. And so if we're going to add up arc lengths, if we added up pressures, we used integral or whatever, it just added up. So the question is, what is this adding up? Are we actually adding up when we do this? Well, let's go back to an example. Let's look at our good friend R equals cosine t and sine t. And let's look at, say, the integral from 0 to pi. Right? So see this as we go from 0 to pi. All right, so we have to start by integrating each one of these things. So the integral of cosine is sine. The integral of sine is minus cosine. And we're going to evaluate that at 0 and pi. Okay, so sine of pi is 0, sine of 0 is 0. This gives us 0. Cosine of pi is -1. So negative 1 is 1. Cosine of 0 is 1. 1 minus 1 is 0. All right, so we just integrated from 0 to pi, and we got the 0 vector. All right, so let's just kind of bring this back for a second. Here's the circle. All right, we're on the unit circle. And we just did this from 0 to pi. So clearly, we're not getting area. Right? We're not getting area because first of all, it's 0. But secondly, it's a vector. So what we're ending up with here is a vector. Okay. So that's not area. So where is this vector 0, 0? That's just this point, right? So what is this? What are we getting? All right. So, oh, you know what? I botched this. It's not 0, 0. It's 0, 2. Because when you subtract -1, you're actually adding 1. Sorry about that. So I get 0, 2. Okay, well, clearly 0, 2 would be better. So again, what is actually getting us? Well, it's a little bit hard to picture graphically, but think about we're adding up all kinds of vectors. So we've got this vector, right? We're adding all those guys up forever. Now, you look at the horizontal pieces of each of these, they end up canceling each other out because we've got positives and negatives. Those cancel, which is why our x ended up being 0. But if you were to take all those y components and add them up, it's not a strict add up because obviously adding up an infinite number of things would, grow forever. But if you kind of break it down and you do your little like differential widths and all that sort of stuff, basically adding up all of those x component or y components, which then gives us 0, 2. So what it's giving us geometrically isn't really useful on its own, but we are doing the same thing that we did before, which is just add up an infinite number of really small things, really small chunks, right? Now, you're going to see how we can use this for arc length. You're going to see how we can use this for some other things. So there are applications to it, but the actual steps of doing the integral, super easy. So there's a lot of lag, huh? The video's way behind my
Yes.
speech.
No, it just like very frequently throughout this session, there's been tons of lag.
Okay.
And the audio shatters. Yeah, it's difficult to understand you.
All right. Well, I apologize. I wonder, it must be my end then, since you're all experiencing it. So, yeah, I apologize for that. Thanks for letting me know, though. I'll see if I can work on it over the weekend to get this to work a little bit better.
Definitely. Thanks, Bruce.
All right. Well, we're pretty much time anyway. And so since there are starting to be some issues or continuing to be issues, I'm going to go ahead and stop. So we'll meet up again on Monday. And like I told you, what we're going to do is kind of move forward and keep talking about the big T and the big N and how they have to do with curvature and talk geometry of space curves. All right. So that's what we're going to do when we back next week. So again, don't forget your homeworks are due, first sets are due Monday night at midnight. But feel free to send me messages and all that. And I will respond this weekend when I get a chance. All right. So with that, I'm going to go ahead and pause the recording.